Hey, Math 206 students, welcome back. Previously, we learned about this concept of basis, right? Remember, that's a linearly independent spanning set. A spanning set, I just want to talk a little bit about a spanning set. You can think of it as a set of building blocks that allows you to create all the vectors within your vector space. Linear independence keeps it as small as possible. So a basis, a linearly independent spanning set then, is an efficient set of building blocks for creating all the vectors in your vector space. So this next theorem is going to give us some information about the existence of bases. So let's let V be a vector space. Then there exists a subset, say capital S, of V such that S is a basis for capital V. This can be paraphrased like this, so we can say it like this. Every vector space has a basis. So that's good, right? What we have then is an efficient set of building blocks for every single vector space out there, right? So bases are going to be extremely important in this class. The proof of this theorem is beyond the scope of this class. When I teach Math 306, I actually do prove it in that class, but we're just going to accept that this is true and move on. So I want to talk. We're going to really explore the nature of bases today. So suppose V has basis, call it capital S, equal to, and I'm going to write out the vectors V1 up through V sub n, and let capital T be a collection of vectors. I'm not claiming that this is a basis here. Let T be the set of vectors, let's call them U1 up through U sub m. Okay? So it's just some collection of vectors living inside V. Now, what I want to do is I'm going to form a matrix. So let's form the matrix whose columns are, so in order, they're going to look like this: U1 bracket sub S, U2 bracket sub S, all the way to U sub M bracket sub S. Right? So what we've got is a matrix whose columns are the coordinates of U1 with respect to X. There's the first one. The coordinates with respect to S of U2, and so on, all the way down to U sub M. Now, in the case, so let's say, in the case that M is strictly greater than N, so let's see now, M is going to be the number of columns that we have in this matrix. N is the number of rows. So in the case that M is greater than N, and I want to give this, let's call that matrix capital A. So in the case that M is greater than N, the homogeneous system, say AX equals 0, is guaranteed to have non-trivial solutions, right? We will have at least one free variable because we've got more rows than more columns than we have rows. So this homogeneous system will have at least one free variable And so that would mean that it has non-trivial solutions. And so we'll have non-trivial solutions. Fine. What that is going to do is it's going to give us, and in fact, let's write out one of these. Yeah, let's how I want to say it. Yeah, fine. Let's say it like this. Conclusion. The equation A1U1 plus dot 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 plus AMUM equals 0 will have a non-trivial solution. So what does that tell us then? It tells us that that collection of vectors right there is linearly dependent. I'm going to summarize that in just a second, but let me say one more thing here. So if in the case that m is strictly less than n, so now we're going to have fewer columns than we will rows. A similar argument shows that the span of T is not equal to capital V. So let me summarize what we just did here. So summarizing. So one, if m is greater than n, then T is linearly dependent. And part two, if m is strictly less than n, then span of T is not equal to V. Right, so these are both important. There's something, now what this is telling us is there's something special about the number n, right? And that's the number of vectors in our basis. So we can kind of combine all of this into a theorem. If S equal to V1 up through V sub n, and T equal to U1 up through U sub m are bases for capital V, then m has to equal n. So what this is saying is any two bases for the same vector space have to have exactly the same number of elements, the same number of vectors inside. And so this leads to a definition, right? Every vector space has this number connected to it. This number, which is the number of vectors, right, that give us a linearly independent spanning set. So, the dimension of V is the number of vectors in a span in a basis. I was always intrigued when I was younger. I was intrigued by this notion of dimension. What is it? What exactly is dimension? Well, now we know. In the vector space setting, dimension, right, is the number of the number of vectors in a basis. The notation, we write DIMV. It's possible that there is no finite basis, so if V has no finite basis, we write dimension, so dim of V equal to infinity, right? So there are. Okay, so now let's take a look at some examples, first of familiar vector spaces and their dimensions. So let's start off with the dimension of Rn. That's exactly equal to n. Why is that? Because we know a certain basis already. For Rn, there is the standard basis, E1, E2, E3, all the way up to En. So because Rn has a basis consisting of n elements, that means that the dimension is equal to n. Next familiar example, let's look at P sub n. The dimension of P sub n is n plus 1. Why is that? Because we know at least one basis for Pn, that is the basis consisting of the polynomials 1x, x squared, all the way up to x to the n, right? And so, because there are n plus 1 elements in the set that I just listed there, right, that tells us that the dimension is n plus 1. The dimension of the set of all m by n matrices is m times n. Why is that? Because there's a basis for m sub n consisting of m times n matrices. Remember, they were these ones right here, E sub ij. That's the matrix that has a 1 in the ijth position and zeros everywhere else. And then, here we go, one more. Dimension of D sub n, that's equal to n. Why is that? Because it has a basis. We talked about a spanning set for it. So matrices that have zeros everywhere except in one spot along the diagonal, right? Take all possible such, and zeros everywhere else, right? All such matrices of this form will be a basis for D sub n, and there are n such diagonal matrices. One example of an infinite dimensional vector space, the dimension of the set of all functions, that's equal to infinity. Okay, so now let's do an example of a vector space that we haven't seen before. So let's let T from R4 to R2 be given by, so I'm going to write down the formula for a linear transformation. It'll be given by T of x, y, z, w equals, and the formula here is going to be x plus y plus z, and y minus w. All right, so here you can check this is a linear transformation from R4 to R2. What I'd like to do, let's find the dimension of the kernel of T. I'm not sure if I've used this abbreviation or this notation before, KER of T. That's the kernel of the linear transformation T. And remember, the kernel is the set of all vectors in the domain whose output equals the zero vector. Okay, so we want to compute the dimension of the kernel. And we know from earlier the kernel is a subspace of R4 in this case. It's always the subspace of the domain of the linear transformation. Right, so we know it's a vector space, we know it has to have a basis, and so what we want to do is count the number of vectors required to form a basis for the kernel of T. All right, so now let's move on to the solution. The first thing I'd like to do, let's write down the matrix. So the matrix of T, that's going to be, so let's call it capital A. It's going to be 1, 0 for the first column, 1, 1 for the next column, 1, 0, and 0, minus 1. Okay, so here's the matrix of T, and so now to find the kernel of T, to identify which vectors are in the kernel of T, what I need to do is consider the homogeneous system that looks like this: 1, 1, 1, 0, and then add another 0 at the end. 0, 1, 0, minus 1, 0. Right? So what I want to do is solve this linear system, the set of solutions to the homogeneous system. That's exactly who the kernel of this linear transformation is. We're almost in reduced row echelon form. I guess I just need to do one row operation here. So I'm going to subtract bottom row from top row. So let's see, it looks like we have two free variables in this case. So let's say x3 equals s and x4 equals t. x1 equals negative s minus t, and x2 equals t. So the general solution to this system looks like this. So we will have a negative s minus t, then we'll have a t, then we'll have an s, and then we'll have a t. Right? So vectors in the kernel of T are exactly the vectors of this form. Now, what I need to do, I'm trying to find a basis. All right, we want to compute the dimension. And so what I want to do is think about what solutions of this form take. And so what I could do, I want to split it like this: minus s 0 s 0 plus minus t t 0 t. Right? I split it into two vectors, the stuff involving the s and the stuff involving the t. This is equal to s times negative 1 0 1 0 plus negative 1 0 1 0 plus t times minus 1 1 0 1. So what is this telling us right here? It's telling us that the kernel of T is equal to the span, so we can say span, of this set minus 1 0 1 0 and minus 1 1 0 1 is equal to the kernel of T. Why is that? Because every vector of this form can be written as a linear combination of these two vectors. Also, since neither, remember, when there's two vectors, to decide whether they're linear independent, all you need to do is check to see whether one is a multiple of the other. And since neither is a multiple, so since the vectors are not multiples of each other, that tells us the set is linearly independent, so the set is linearly independent. So what does that tell us then? This set right here is a basis. And so the dimension of the kernel of T is equal to 2. We have a basis consisting of exactly 2 elements. That tells us then that the dimension. Okay, let's discuss a little bit more about dimension and bases and so on. This next theorem has a name. It's called the plus-minus theorem. All right, so if you read your book, it'll say plus-minus theorem when we're making use of it. And it goes like this. So let's let S equal to, let's go V1 up through V sub K, not claiming that it's a basis at this moment, right? So it's just, it's some set in our vector space. Now, part A, if S is linearly independent, and U is not in the span of S, then the set consisting of V1 up through V sub k plus U, this is the plus part, is linearly independent. So what this says then, if you start off with a linearly independent set and choose any vector outside the span, throw that vector into the set remains linearly independent. So, right, so there's the plus part, here comes the minus part. So if, let's say V sub I lies in the span of all the vectors except for Vi. So I'm going to go V1 up through V sub I minus 1, V sub I plus 1 up to V sub k. All right, so if V sub I is a linear combination of all the other vectors, then it's redundant. We can delete it. There's the minus part. So then, let's say this, span of S is equal to the span of V1, all the vectors except for V sub I. So V1 up through V sub I minus 1, V sub I plus 1, up to V sub k. So if you have a vector that lies in the span, then you can delete it and it won't affect the span. Right? The set consisting of all the vectors except for V sub I still span the entire set, or give you the same span. So here's an application, this example here. So, so let's show that the set consisting of the following matrices. So it's going to be a 1, 0, 1, 0, and 1, 1, 0, 0, and 1, 1, 1, 1 is linearly independent. Right? So we've got this collection of vectors in M sub 2, 2, and we want to show that our set is linearly independent. Now, the way I'm going to start, and I want to use the plus minus theorem here. And so let's call these matrices A, B, and C. So first thing to note, AB is linearly independent. When you have two vectors, it's very easy to decide whether they're linearly independent or linearly dependent. If one is a multiple of the other, then it's dependent. If not, then it's independent. So notice that A and B are not multiples of each other. There's no way to multiply A times some constant and get the matrix B. So this set is linearly independent. So I'll just say something like this. A is not equal to T times B. Okay, so now I want to use the plus minus theorem, and I'm going to use a part A. I've got a linearly independent set, and part A tells us when we can throw another vector into the set and remain linearly independent. So what needs to happen? We need to make sure, in this case, that C is not in the span of A and B. So let's think about the span of A and B. It'll be some number, some constant times the first matrix, plus some constant times the second matrix. And notice what happens. If you multiply this matrix by a constant plus this matrix by a constant, the bottom right will always be 0, which means that you cannot get this matrix as a linear combination. Right? So we'll say note, check, C is not in the span of A and B, so A, B, C is linearly independent. So the plus minus theorem, part A, allows us to insert a vector into our set and remain linearly independent. Now, I'll do a couple more facts. This one really captures the idea of dimension. So theorem So suppose the dimension of V equals n, and what? Let's let S equal V1 up through V sub n. Okay, so I'm not claiming it's a basis right at the moment. I'm just saying suppose that we have a vector space of dimension n and that we happen to have a set consisting of exactly n elements. What this theorem is going to do is it's going to cut the work required to show that we've got a basis in half. Remember, if you've got a basis, it needs to be linearly independent and it needs to span. Right? So there's two things to check. If S is linearly independent, then span of S is equal to V. So if you happen to be able to show that your collection of n vectors is linearly independent, then you're guaranteed that it spans the entire set. Part B, if if span of S is equal to V, then S is linearly independent. So, what is this telling us? If you want to identify a basis, you already know that your vector space has n elements, so you've got to work with sets that have n elements. If it happens to be linearly independent, then you don't need to check to see whether it spans. You're guaranteed it spans. If you happen to know that the span is equal to all of V, you don't need to check that it's linearly independent. You get that for free. Right? So this theorem allows us to cut the amount of work used to identify bases in half. All right, so I want to finish off with a discussion of how dimension works with subspaces. And so suppose W is a subspace of V where the dimension of V is equal to n. Right? Now, if, let's say T equal to W1 up through W sub M, remember, W is a vector space, and since it's a subspace, if T, that means that it has a basis. So if this is a basis for capital W, that means that it's linearly independent. Inside V, we can have no more than n linearly independent vectors. So if T is a basis for W, then M has to be less than or equal to n. If M is equal to n, then by our previous theorem here, so remember, it's a linearly independent set consisting of n vectors. That means it has to span. So then by part A of our previous theorem, so part A of the previous theorem, T is a basis for capital V, and so we have W equals the span of T, which equals V, which means that W has to equal V. Let's collect that in a theorem. So if dimension of V equals n and W is a subspace of V. The first thing, right, so part A, what we showed here, the dimension of W has to be strictly less than or equal to, I shouldn't say strictly, the dimension has to be less than or equal to the dimension of V. Second, part B, if, or let's say it like this, if and only if, so the dimension of W equals the dimension of V if and only if W is equal to V. Right? So subspaces have to have dimension that is less than or equal to. If they happen to have equal dimension, then you know that they're equal. Okay, that's a good place to stop.